Welcome back. This is part two of the Maths and Philosophy session at Oxford Mathematics' online open day. Now, in part one, we've been talking a little bit about one of Zeno's paradoxes, and you may recall that it involved a race between Achilles here and Bellerophon the tortoise. In this part of the session, we're going to look a bit more closely at some of the mathematical and philosophical issues surrounding this race. In the course of doing so, I'm going to invite you to think a bit more carefully about the notion of infinity, and I'm going to introduce you to some thought experiments involving what we're going to call infinity machines. So if that's not how you want to spend the next 15 minutes or so, do feel free to skip ahead to part three, where I'll say a bit more about some of the degree courses in mathematics and philosophy that we offer here at Oxford. So back to the race involving Achilles and Bellerophon then. We closed part one with two questions. So I wanted to know how long it was going to take Achilles to catch up with Bellerophon, and also how far Achilles has travelled. So let's take that second question first of all. And one way to think about this involves an infinite series. So think about the distance s that Achilles travels. Well, that distance can be given by adding up all the different lengths Achilles runs. So first of all, Achilles runs 100 meters. Then he runs 10, then 1, then 1/10, and so on and so on. And so if we add up all of those, we get a series of a kind you might have met before, namely a geometrical series. And it turns out that this one is convergent, so it sums to a finite number. And that number, s, is given by a certain formula you may have met before. So what we look at is we look at the number a, which is the first term in the series, in this case 100. And we also look at the number r, which is the ratio between the terms, in this case 1/10. And the sum to infinitely many terms, s, is given by a divided by 1 minus r. So in this particular case, we're taking 100 and we're dividing it by 1 minus 1/10. So dividing by 9/10 is like timesing by 10/9. So 100 times 10/9, well, a little bit of multiplication, we find that's 111 meters and 1/9. That's how far Achilles has to run before he catches up. How long does it take him? Well, we could think of that as another geometrical series if we want to. So the first run is going to take 10 seconds. Then the next one, just 1 second, 0.1 seconds, 0.01 seconds. And when you write it using decimals like that, it's sort of just obvious that that geometrical series is going to converge, and in particular it's going to converge to 11.1 recurring. In other words, it's going to take Achilles 11 seconds and 1/9 to catch up. And actually, if you don't want to bring infinite series into this problem, you don't have to. So an alternative way to come to these answers is simply to think about relative velocity. Achilles is going at 10 meters per second and Bellerophon at 1. So that means that the relative velocity, which Achilles is catching up with, is 9 meters per second. And he's got to catch up that initial 100-meter head start Well, 100 divided by 9, that's going to give the time it's going to take him, which is, once again, 11 seconds and 1/9. And in that time, going at 10 meters per second, the distance s Achilles goes is, as before, 111 meters and 1/9. All right, so using A-level or equivalent mathematics, we seem to have solved one of Zeno's paradoxes. And I suppose, obviously the theory of geometrical series wasn't quite so well developed back in 450 BCE. On the other hand, presumably these ideas about relative velocity may well have been available to Zeno or Aristotle. But interestingly, not everyone is quite fully satisfied with this kind of response. So here's what Max Black, an American philosopher writing around about 1960, says about this way of solving Zeno's paradox. This bit of mathematics, with which he is well appraised, he says, well, that tells us correctly when and where Achilles and the tortoise will meet, if they meet. But it fails to show that Zeno was wrong in claiming that they could not meet. So the question I want to look at now is, why is this American philosopher writing not in 450 BCE, but around 1960, still worrying about this one of Zeno's paradoxes? Well, to answer that question, I want to begin by thinking a little bit more carefully about infinite series. And to begin with, I want to think about what we mean when we say that a certain geometrical series of the form a plus ar plus ar squared, etc., infinitely many terms, adds up to a finite number s. And if you ask mathematicians about this, they typically won't tell you that what that means is, well, you have to do infinitely many additions. You start with a, and then you add up ar, and then you add to that ar squared, and keep going on in that way. And the result of performing these infinitely many additions is that you get s. And I suppose if you think about it, even if you got the right answer, none of you added up infinitely many numbers one by one. So that can't be exactly what we mean by this. So what then do we mean? Well, I suppose you got the value s perhaps by applying a certain formula from formula booklets or whatever you might be familiar with. So let's have a little think about where that formula comes from. And to do so, it's useful to start with the finite sum to just n terms. So suppose we take this geometrical series and we look at the first n terms added up. So that's Sn, which is a plus ar, and then adding up all the terms up to ar raised to the n minus 1. Now that finite sum is equal to the expression we have on the slide here, namely a into 1 minus r to the n all over 1 minus r. And you can see that with just a little bit of algebra. So if you times both sides by 1 minus r, there's going to be lots of cancelling on the left-hand side, and that's going to drop out fairly easily. So Sn gives us the finite sum of the first n terms. What about the infinite sum? Well, again, if you ask a mathematician, what they'll say is that really an infinite sum is a kind of limit. So to find the infinite sum s, what we do is we take the finite sum Sn and we let n tend to infinity. And what you can see is that as n tends to infinity, provided r is less than 1, this r to the n term is going to disappear. And so the infinite sum is the term you're familiar with, namely a divided by 1 minus r. So you might well think that where infinity is coming in is in this business of taking the limit of letting n tend off to infinity. But now, if you ask a mathematician, but what does that really mean? That the limit as n tends to infinity of Sn is this particular value, a divided by 1 minus r. What is slightly surprising about the answer you'll get is that it nowhere involves the infinitely large. So what they'll tell you is along the lines of, well, if you add up a big enough finite number of terms in the series, you can get as close as you like to the limit, to a divided by 1 minus r. A little bit more carefully, what they mean is that you give me any margin of error you like. It can be as small as you like, but it has to be a positive real number. Then I can find some perhaps very large positive integer big N, but nonetheless a finite positive integer big N. And if I add up more than big N many terms, I'm going to come within your margin of error of the limit of a divided by 1 minus r. So don't worry too much about the technical details here, but what's really striking is that on analysis, when we're looking at infinite series, infinity seems to drop out altogether. Our account of what it is for an infinite series to add up to a divided by 1 minus r is ultimately analysed in terms that nowhere involve the infinitely large. So that brings us back to our race with Achilles and the tortoise. We don't really add up infinitely many numbers. Why then think that Achilles can succeed in running infinitely many distances in order to catch up with the tortoise? Here's how Black puts it. He says that the logical difficulty is that Achilles seems called upon to perform an infinite series of tasks. And it does not help to be told that the tasks become easier and easier or need progressively less and less time in the doing. His task remains just as hard, for he still has to perform what seems to be logically impossible. So this is Black's doubt then about Achilles catching up with Bellerophon the tortoise. Black seems to think that there's some sort of logical impossibility, some sort of logical problem in performing an infinite series of tasks, running these infinitely many distances. So why should that be? Well, to try and illustrate the logical difficulty with doing infinitely many things, Black invites us to consider a thought experiment involving what he calls infinity machines. So the first infinity machine we're going to consider is going to be called alpha. And all that alpha is, in fact, is a robotic arm. And alpha has been assigned a simple task, really. What alpha wants to do is alpha wants to take some marbles on this chute on the left here, and alpha is then going to move them over to the chute on the other side. And I guess because alpha is meant to be an infinity machine, the number of marbles alpha is trying to move is going to be infinitely many. So you've got infinitely many marbles here on the left-hand side. So how might alpha succeed in this task of moving infinitely many marbles from one side to the other? Well, actually, it's very simple. What alpha is going to do is, first of all, just pick up the first marble. And alpha is slowly going to pick it up and move that to the other side and drop it off. And alpha is going to spend 5 minutes doing that. And then alpha is going to have a 5-minute rest. Okay, Next, alpha is going to repeat with marble number 2. But this time alpha is going to go 10 times quicker. So alpha is going to pick up marble number 2, move it to the other side, drop it off. The moving's only going to take 30 seconds this time, and then once again alpha is going to have a rest, but just for 30 seconds. Now marble number 3, alpha picks that one up, 10 times quicker again, so just 3 seconds to get that over, and then a 3-second rest. And then alpha's going to just continue in this way. So you think, well, how long is it going to take alpha to move all infinitely many of the marbles? And I suppose this is including the rests. The first marble takes 10 minutes. The second marble takes 1 minute. The third, a tenth, and so on. And so actually this is a geometrical series that we've already added up. And we know that in 11 minutes and 1/9, so within 12 minutes, alpha will have succeeded in moving the infinitely many marbles. Well, I guess, practically minded sorts might have objections at this stage. Isn't the motor going to overheat? And isn't the arm going to have to go faster than the speed of light? And perhaps can we think of something a bit better and more useful to do with this infinitely powerful machine? Now, Black considers this kind of objection, and he sorts of thinks that they're missing the point. So here's how he replies. He says, "We are dealing with the logical coherence of ideas, not with the practicability of mechanical devices. If we can conceive of such a machine without contradiction, that will be enough." Now, I think if you're not already a trained philosopher, this reply can be a bit puzzling, because you might think, well, we've been presented with some pretty decisive objections against trying to build this infinity machine alpha. But it's important to remember here that Black doesn't want to build an infinity machine. Rather, Black is interested in whether there's some sort of logical problem in performing infinitely many tasks. And for Black's purpose, it's important to make a certain distinction. So we need to distinguish between these two things. On the one hand, physical impossibility, and on the other, conceptual incoherence. So take going faster than the speed of light. That's a good way of illustrating the difference here. So the physicists tell us there's a certain speed. It's about 3 times 10 to the 8 meters per second. And you can't exceed that speed. It's just physically impossible to do so. It's incompatible with the laws of nature to go faster than that particular speed. So certainly then, it's physically impossible. Is it also conceptually incoherent? So you might imagine theoretical physicists describing alternative universes with different laws of nature. Perhaps in these universes, some of the fundamental physical constants, like the speed of light, take different values. In doing so, have they somehow baked in a contradiction into their very description of that alternative universe? That's not so obvious. So it's not so obvious that it's just the very description of a system where bodies can travel faster than this particular speed is somehow contradictory. And so whether it's conceptually incoherent to exceed 3 times 10 to the 8 meters per second is at least debatable. Now, what about alpha? So Black agrees with right-thinking people that alpha is physically impossible. Just like going faster than the speed of light, you can't build a machine like alpha. On the other hand, is alpha conceptually incoherent? Does the very idea of alpha somehow include a contradiction? And strikingly, Black thinks the answer there is also yes. Somehow, in describing this machine that can do infinitely many things, we've given a contradictory description. So why might we think? Why might we think that? Where's the contradiction lurking in alpha? Well, to bring out the issue, Black invites us to consider another infinity machine. And once again, it's just a robotic arm. And this one we're going to call beta. And in many ways, beta is just like alpha. So beta also wants to move marbles around. But this time, beta just wants to move a single marble over from one side to the other side. And beta does this in exactly the way you would expect it to. So beta simply picks up that marble. And over the course of 5 minutes, beta moves that over to the other side. Beta is then having a rest, and during this 5-minute rest period, unfortunately, something then puts it back again. So beta, still determined, I guess, to get the marble over there, picks it up a second time, and going 10 times quicker in the course of 30 seconds, moves it over to the other side. But while beta is having a 30-second rest, something moves it back again. So beta has a third go, 10 times quicker again, and moves it back. But then, again, operating 10 times quicker, something puts it back again. And this process continues, speeding up by a factor of 10 each time. So you might think, well, can beta succeed in moving this one marble over? And Black reasons in this kind of way. Presumably, beta's task is no harder than alpha's. If alpha can succeed in moving infinitely many marbles over to the other side, why can't beta get its marble over to the side it wants it to be on simply by moving that marble infinitely many times? The trouble emerges, though, when you think about, well, what is it that's putting that marble back again? And I suppose the way we might think about this is that really we've got a second machine in the picture, and this one we might call gamma. And you might think of the situation between beta and gamma being that what beta wants to do is get the marble over onto this side, and what gamma wants to do is get the marble over onto the other side. So what's going to happen is that the marble starts over on gamma's side. Over the course of 5 minutes, beta moves it over to beta's side. In the next 5 minutes, gamma puts it back again. So now we run that whole process again 10 times quicker. In 30 seconds, beta moves it over here. In another 30 seconds, gamma moves it back again. And then 10 times quicker again, 3 seconds to get over here, 3 seconds to get back again. And then what happens in the end then? So where's this marble going to end up? So within 12 minutes, in 11 minutes and 1/9, this process has run to completion. So let's try and bring this all together to try and get a sense of what the conceptual problem might be in performing infinitely many tasks. Let's suppose, as must be the case, that Achilles can catch up with Bellerophon the tortoise. Well, that goes to show that there's no conceptual incoherence in performing infinitely many tasks. Achilles can run infinitely many distances simply because each one gets shorter and shorter, takes less and less time to do, and sometimes an infinite series has a finite limit. Well, if that's right, setting aside the physical impossibility, it also seems to be the case that alpha, in a similar sort of way, can succeed in moving infinitely many marbles because each one takes less time to move. Now, Black says, if alpha can do that, beta can also succeed in its task, and therefore the marble must end up on beta's side. But then you get to thinking, well, isn't gamma just a mirror image of beta? If beta can succeed, so too can gamma. So in fact, the marble ends up not on beta's side, but on gamma's side. So where then does the marble end up? Well, I'm not going to delve into that question any further, but if it's something you're interested on following up on, I have two recommendations for you. So the first is Max Black's article, which we've been talking about today, which is called Achilles and the Tortoise. And that article appears in a volume containing lots of interesting thinking about Zeno's paradoxes, edited by Wesley Salmon. So that completes part 2 of this session. If you'd like to hear a bit more about the undergraduate courses we offer, come back for part 3.